This is Laplace transforms, and in this video we will be talking about the inverse Laplace transform. So when we first defined a Laplace transform, we had a function f of t, and we mapped that into a function capital F of s, which was our Laplace transform. In this video, and when we find the inverse Laplace transform, we will be given that Laplace transform and finding a function f of t. And this is called inverse mapping. And that's exactly what we are going to be doing here. So let's go ahead and take a look at this definition. Given our Laplace transform capital F of s, if there is a function f of t that is continuous on 0 to infinity, and it satisfies our definition of a Laplace transform, then we say that f of t, small f of t, our function, is the inverse Laplace transform of our Laplace transform capital F of s, and we employ this notation, and it's your typical inverse notation. Let's talk about the linearity of the inverse transform. Basically, we inherited these from the linearity of the Laplace transform, so we inherited properties from the Laplace transform linearities. Okay, and here we have that our inverse Laplace transform of f sub 1, and f sub 2 exist, and they are continuous. This is what we assume. They are continuous on 0 to infinity, and we have c as a constant. So here you can see that we have the inverse transform of the sum of two Laplace transforms is equal to the sum of the two inverses. Likewise, if we have the inverse Laplace transform of a constant multiplied by a Laplace transform, that is equal to the constant multiplied by that inverse transform. So they're pretty straightforward. Let's go ahead and take a look at this example and see what we have here. Let's also keep in mind that we will use the second column of the, I think it was called the basic, but the Laplace transform table. These will really help us. Some of these get complicated, and that table is really going to help us with some of our algebra and trying to identify what to do, help us find what to do. Okay, so let's look at our first example. We are given that the Laplace transform is 4 divided by s squared plus 9, and we are looking for the inverse Laplace transform. We're seeing something very similar to the sine function. I'll just kind of show you on this one from the second column of the table. We have that we can see that when f of t is equal to the sine of b times t, f of s, which is our Laplace transform of our function of s, is equal to b divided by s squared plus b squared. So that's from our table. So now with that, let's try to come up with this form. Let's say that the inverse Laplace transform of 4 divided by s squared plus 9 of t is going to be equal to 4/3 multiplied by the inverse transform of, and this 3 is going to come from what I'm going to bring here, this 3. Let's go ahead and erase this. And we have 3 divided by, and we want to get this s squared plus b squared. So we needed that b of 3. And there's our b squared of t. And now we can see that that's 4/3 multiplied by the sine of 3 t. So hopefully this helps with that. Okay, just want to do one thing here. There's our b and there's our b. Okay, let's look at our second example. Our Laplace transform is 3 divided by 2s plus 5 all cubed. So we recognize from our second column of our Laplace transform table that if we have f of t equal to e to the at, t to the n, we have our Laplace transform as n factorial divided by s minus a to the n plus 1 power. So using that as an example, we can now say that the inverse Laplace transform of our f, capital F of s, and that is of t, is equal to, and so now let's go ahead and take a look what we need. So we can move that 3 out with our linearity. So we have that 3, and then let's go ahead and write this. Now we have 1, and we would like to have s minus a here. So we are going to divide this by 2, and of course that would be 2 cubed, so we'd have to multiply by 2 cubed. So we have 2 cubed here, and now we have s plus 5 halves all cubed of t. Now we have our form, 3 divided by 8. Now we do need to look at our form here. See if I can make that a little bit smaller. Okay, so I can also move this down a little bit. That's going to help us. So now we have the inverse transform divided by s plus 5 halves cubed. So as you can see here from our formula, n plus 1 is going to be equal to 3. So n is equal to 2. So we will need a 2 factorial in the numerator. So we will have to have a 2 factorial in the denominator. So this is going to be equal to 3/16. Here's our form. So here we have n equal to 1, and we have a equal to a negative 5 halves. So we have 3/16. Whoops. T squared e to the at, which we would have a negative 5 halves t. Okay. Let's take a look at our next example. We have the Laplace transform of s is equal to 1 divided by s to the 5th. So looking at the second column of our table, we have that when f of t is equal to t to the n power, the Laplace transform is equal to n factorial divided by s to the n plus 1 power. So trying to come up with this form, we can see that n plus 1 is equal to 5. So n is equal to 4. So we have that the inverse Laplace transform of 1 divided by s to the 5th of t is equal to, and using this formula here, we're going to have, leave a little blank there, Laplace transform, and we will have s to the 5th power, because it's s to the n plus 1 power, in the denominator, and that will be of t. Now we do need n factorial here, so n factorial is equal to 24, so we can put 24 here, or 4 factorial, and 1 divided by 4 factorial, and we come up with 1/24 multiplied by t to the 4th power. Okay. Let's take a look at our next example. Determine the inverse Laplace transform of this function. So let's go ahead and do some algebra, and then we could go ahead and take a look at the table and see if we see something we can work with. So here, let's go ahead and try to complete the square in the denominator, since everything in our table that has higher powers of factors has squares or cubes. So let's go ahead and try to complete this square. So what we have here is s squared plus 4s plus 4. That will give us that perfect square of s plus 2. And then we still have a plus 9. So we have 2, and let's go ahead and factor that trinomial s plus 2 all squared plus, and we're going to have another square here in our formula, and there is our 3 squared. So now we begin looking at the table. Let me go ahead and write down from the table 2 of the functions we are looking at. So if f of t is equal to e to the at cosine of bt, we are going to have the Laplace transform is s minus. So we have that difference in the numerator, and we need that difference here in the s minus a spot. So that'd be s minus a squared plus b squared. Now we're also going to have just a constant in the numerator, because we probably aren't going to be able to just get a subtraction there, a difference. So we also take a look at f of t equal to e to the at sine of t. And here we have just b in the numerator. So we will probably need both of these, and then we have that same denominator, which is going to help us, s minus a squared plus b squared. So we can pretty much see that our b is going to be equal to 3, but we need s plus 2 in the numerator. We need that s minus a. So let's go ahead and break apart that numerator. So factoring a 2 out, we can have s plus 2, and then that would give us our 2s plus 4, but we're going to need another 12. And let's go ahead and keep that same denominator. Okay, and so now we can see that, and let's go ahead and take this 4 times 3, which is our 12, so that we have our b noted in that numerator. Then, of course, we have our s minus a here, and I'm going to go ahead and highlight those. So that is what we're looking to do, and I think we've got it. So now let's go ahead and use those two. We can say that by linearity of the inverse Laplace transform, the inverse Laplace transform of 2s plus 16 divided by s squared plus 4s plus 13 of t is going to be equal to, and let's start here. This is going to be equal to 2 multiplied by the inverse transform of s plus 2. So we factored this 2 out already. S plus 2 divided by s plus 2 squared plus 3 squared. And that is of t plus, now let's go ahead and factor that 4 out, or use our linearity principle, multiplied by the inverse transform. And here we just have our 3 now in the numerator, and we have s plus 2 squared plus 3 squared of t, and we are already set up with our form. You can see here that a is equal to 2, negative 2, and we have that b is equal to 3. And same here, we have b is equal to 3, and a is equal to negative 2. So this works out really nicely for us. And we have what we need. So we have that that's equal to 2e to the negative, negative 2t, that's our at, cosine of bt, which is 3t, plus 4e to the negative 2t multiplied by the sine of 3t. Okay. Now, for our more complicated problems, of course, we're going to need to complete the square, and I should probably write that here to get what we want. We're also going to be using partial fraction decomposition. So it's really important that we quickly review this method. So we do have Q is a polynomial that can be factored into a product of distinct linear factors. So we have no repeated. So how we do that is that we have each one of our r's, which are real number, and we factor Q of s as shown there. And the partial fraction expansion has this form. So we will be using capital A in the numerator over each linear factor. When we have repeated factors, as you can see here, s minus r to the m power, how we will handle that is we will write s minus r and then s minus r squared and so forth all the way up until we get that s minus r to the mth power. Okay, so also we can see here that this is the highest power of s minus r. So m is that highest power. Okay, what if we have quadratic factors? So we can see here that if we have quadratic factors, cannot be reduced to linear factors. So we do have to make sure that we have that form. So m is the highest power of this quadratic factor. So that would have a power of m. And how we would do that is we would have a constant multiplied, of course, this is our review here, multiplied s plus d1, and we would have constants for c and d going all the way up to m of them. This is the form we are going to use since we are working with Laplace transform. So this will be how we are going to do that. So as you can see, there are m factors of this quadratic. We will write it to the first power, raise it all to the second power, and so forth, all the way till we get to the mth power. Let's see what we have here in our first example. As you can see, we have two distinct linear factors, non-repeated linear factors. So that would be our first case. And what we are doing is we are just going to look at that expression, so negative s minus 7, because they just wanted the expansion in this problem. We are not doing anything with Laplace transforms or inverse transforms. So we can see that negative s minus 7 divided by s plus 1 multiplied by s minus 2. And we're going to say that's equal to a over s plus 1 plus b over s minus 2. That's that first form. Okay, so now multiplying the numerator and denominator by this factor, what we come up with is negative s minus 7 is equal to a times s minus 2 plus b multiplied by s plus 1. So basically, just to remind you, we had s plus 1 multiplied by s minus 2. These would cancel. These would cancel. That's why we just have that, and so forth. Okay? So that's where we came up with that. And if you need to take a moment to review that, you can. So now let's go ahead and see if we can solve this. So what I like to do is I like to say that negative s minus 7, when s is equal to 2, whoops, I forgot to put that. Since these are polynomials, of course, the domain is all reals. So we're going to let s equal to 2. And there are several ways you can do this. If you already have a method, that is just fine. So that is going to be a times 2 minus 2. Of course, that's going to be 0 plus b times 2 plus 1. Okay, and we will simplify this later. So we have negative s minus 7 is equal to 3b. And I forgot to put negative 2 in there. So we have negative 9. And so we have b is equal to negative 3. Let's do the same thing. Let's let s equal negative 1. Again, if you have another way that you solve these, that's okay. So we have a negative 1, which a positive 1 minus 7 is equal to a times negative 1 minus 2 plus b negative 1 plus 1. Of course, we planned it that way. So we have a negative 6 is a negative 3a, and a is equal to 2. So that's a nice fast way if you don't already have a method. So therefore, what do we have? Therefore, negative s minus 7 divided by s plus 1 multiplied by s minus 2 is equal to 2 over s plus 1 minus 3 over s minus 2. So we can decompose a fraction into partial fractions, and that's exactly what we did here. Let's try another one. These instructions are not correct. We are just going to determine the partial fraction expansion. Okay, so as you can see here in this next example, the denominator has one linear factor and one irreducible quadratic factor. So we can go ahead and write this as a over s plus 2 plus we'll have b times s, since alpha is equal to 0, and since we have beta equal to 3, so we have s squared plus 3 squared. We want to have 3 times c. Oops, let me do that in green. Goodness. We'll go ahead and write it that way. Okay, so now what do we have? we'll have negative 5s minus 36, multiplying every term by this, that product of those factors. So we will have a multiplied by s squared plus 9 plus bs plus 3c multiplied by s plus 2. Let's go ahead and let s equal to negative 2. So you can see here that we have negative 5 times negative 2 minus 36 is equal to a multiplied by negative 2 squared plus 9. So you can see that we have a negative 26 is equal to 13a, and we have a is equal to negative 2. Let's go ahead and let s equal to 0. That will allow us to lose b so that we can solve for c. So when s is 0, we have 0 minus 36 equals a, times 0 plus 9 plus b times 0 plus 3c multiplied by 0 plus 2. I won't use those zeros next time. That's very confusing. 3c times 2 would give us 6c. Since we have a equal to negative 2, we have that negative 36 is equal to negative 18 plus 6c, and I'll let you do that math. That would be c equal to negative 3. And I'm just going to put little circles around here. And now we are able to, we could do the same thing. And now let's let s equal to 1. So when we let s equal to 1, we have nice, simple computations. So again, we are using this equation right here. And you could let s be anything you like. So we have negative 5 minus 36 is equal to a times 10 plus, and let's just write 10a. So it makes it really easy. Plus b plus 3c multiplied by 3. So we have a negative 41 equals 10a plus 3b plus 9c. We'll go ahead and use these two. So we have a negative 41 is equal to negative 20 plus 3b minus 27. End up with 6 is equal to 3b, so b is equal to 2. So we can say that negative 5s minus 36 all over s plus 2 multiplied by s squared plus 9 is equal to, and we have a negative 2 for a, and you see that we have that right there. So we have a negative 2 over s plus 2, and then we have a b times s, which would be a 2s divided by s squared plus 9. And we do want to have separate fractions. And then we have minus, and that's our c times 3. So we have a negative 9 divided by s squared plus 9. Now we do want pretty simple fractions, so you may see some solutions that look like this. So we would have a negative 2 multiplied by a 1 over s plus 2 plus 2 divided by s squared plus 9 minus 3 divided by 3 over s squared plus 9, keeping that same format that we had when we started. Whoops, wow. Okay, so moving on to the next example, and I will stop doing all of that, and we will just square that off. Now, let's take a look at this next one. Again, we are just looking for the partial fraction expansion. And we have s divided by s minus 1 multiplied by s squared minus 1. So we can already see here that we have s divided by s minus 1, s minus 1, s plus 1. We have that difference of squares. So as you can see, we have s divided by s plus 1 multiplied by s minus 1 squared. So we have a repeated linear factor along with a non-repeated. Using our formula, we can say, let's just go ahead and put this down here. We can say that we have that equal to a over s minus 1 squared, that's that repeated, plus b divided by s minus 1 plus c divided by s plus 1. Okay? So now what we want is this to be on our left-hand side so that we can show our algebra. It's not a problem. Okay, now multiplying both sides by that denominator, s plus 1 multiplied by s minus 1 squared, we end up with s is equal to a times s plus 1 plus b times s plus 1 s minus 1, which would be s squared minus 1 if you want to write that, plus c multiplied by s minus 1 squared. And we could go ahead and write s squared minus 1 if we want, but I kind of like it like that. Okay, so now let's go ahead and let s equal 1. And so if s equals 1, we get 1 equal to, and let's go ahead and try to keep this a little simpler this time. We lose this term, so we get 2a, and we also lose this term. So we see that a is equal to 1/2. Okay, now let's let s equal a negative 1. And of course, we will lose these two terms. And we have negative 1 is equal to c times negative 2 squared. So negative 1 is equal to 4c, and c is equal to negative 1/4. So with that, we could let s be anything we'd like. I'd like to go ahead and just let s be 0 if we want. And makes it easy. So we have 0 is equal to a plus, and that would be a negative b, minus b plus c. And we have 0 equals 1/2 minus b minus 1/4. So we can say b is equal to 1/4. So therefore, we want to go back to our original function that was given to us. We can say, so s divided by s minus 1 multiplied by s squared minus 1 is equal to our a, which is 1/2 multiplied by 1 over s minus 1 squared, plus 1/4 multiplied by 1 divided by s minus 1, minus 1/4 multiplied by 1 divided by s plus 1. We could leave it like that if you'd like. It looks just fine. You could use parentheses here or just leave it like that. Okay, let's see what we can do with what we have learned so far. And here we are going to find our inverse transform of this given rational function, capital F. Here we can see our denominator has a linear factor s plus 1 and then a repeated factor s plus 3. So let's go ahead and work on that partial fraction first. So we can say that 5s squared plus 34s plus 53 divided by s plus 3 squared multiplied by s plus 1 is equal to, and now we're going to say a divided by s plus 3 squared plus b divided by s plus 3. We've taken care of that repeated linear factor, and c divided by s plus 1. Now multiplying both sides by this denominator, we now see that we have 5s squared plus 34s plus 53 is equal to a times s plus 1 plus b multiplied by s plus 3 times s plus 1 plus c multiplied by s plus 3 squared. Okay? So I'm going to go ahead and let s equal, I can start with a negative 3. And we will lose these two terms, which will be very nice. So if s is negative 3, we have 9 times 5. That's 45 minus, well, I just plugged it into my calculator, and I ended up with a negative 4 is equal to a negative 2a. So a is equal to positive 2. Let's go ahead and let s equal a negative 1, and when s is a negative 1, we have 5 minus 34 plus 53, and we get 24 is equal to 4c. So c is equal to 6. So it doesn't really matter. We could just say s equal to 0. Again, you can do what you want. So if s is 0, we get 53 equals a plus 3b plus 9c. And using our a equal to 2 and c equal to 6, we have that. Negative 3 is equal to 3b, so b is equal to negative 1. So now we can say, and we're going to be working on this using our Laplace transform table in a moment, but what we can say here so far is that the inverse transform of 5s squared plus 34s plus 53, all divided by s plus 3 squared multiplied by s plus 1 of t is going to be equal to, and here we're going to be putting our a in here, so that would be 2 multiplied by the inverse transform of 1 over s plus 3 all squared. That's this term right here. Of t minus, and let's go ahead and put b in. B is a negative 1, so we can just keep that minus. The inverse transform, and we see this here, which is 1 divided by s plus 3 of t plus, and now we'll use our c equal to 6, and you can see that we will have 6 multiplied by the inverse transform of 1 over s plus 1 of t. Now, these are all of our exponentials. We can use the table, and I can tell you that that would be when f of t is e to the at, we have our Laplace transform equal to 1 divided by s minus a. So this will help us here and here. Now, taking a look at this function, we have a second place in our column, and we can see that we have e to the at multiplied by t to the power of n. And here, our Laplace transform is going to be equal to n factorial divided by s minus a to the n plus 1 power. So these are going to help us with both of these. Make that just a little bit smaller. And then we will need this one here. Okay, so let's give that a whirl. So we can see here that we have 2 multiplied by t to the first power, e to the negative 3t, since we have that a is equal to negative 3. And here we have that n is equal to 1. And then what we have here, just move this down. For our next one, we have minus e to the negative 3t. There's our minus. And of course, our a is equal to negative 3. And now we have our 6. So we have plus 6. And there's our 6. And here, our a is equal to negative 1. So we have 6e to the negative t. Okay, and that leaves us with one last problem. Find the inverse transform of f. And as you can see here, our partial fraction has the form of a over s cubed. So this is a repeated linear factor plus b over s squared plus c over s plus our non-repeated linear factor of s minus 2. So let's go ahead and say that 7s cubed minus 2s squared minus 3x plus 6 is equal to a multiplied by s minus 2 plus bs multiplied by s minus 2 plus cs squared multiplied by s minus 2 plus ds cubed. We can let s equal 0, which is going to wipe out all of these terms with an s in it. An s is a factor. And we end up with 6 is equal to negative 2a, so a is equal to negative 3. Now we can go ahead and let s equal to 2. And if we let s equal to 2, we will come up with 48 is equal to, and this is the only term we have left, and so that would be 2 cubed, which is 8. So we had an 8d, and d is equal to 6. Now we still need to find b and c. Here, let's try doing something. Now, let's match coefficients. So we will go ahead and plug these values of s equal to, leave our values of s in there, and we will plug our d and our a in, okay? So we will use a equal to negative 3 and d equal to 6 to write this, okay? So now we're going to have 7s cubed minus 2s squared minus 3s plus 6. So a is negative 3. So we're going to have a negative 5. We're not. We're going to have a negative 3 times s minus 2 plus bs times s minus 2. See if I can make this a little bit smaller. Plus cs squared multiplied by s minus 2, and we have our d is equal to 6, so we'll have 6s cubed. So now if we match the coefficients for s cubed, we have that c plus 6, so you can see this is going to be an s cubed factor. We have cs cubed here, and we also have a 6s cubed, okay? So we're going to have, and we have a 7s cubed here. So we know that 7 has to be equal to c plus 6. So c is equal to 1. So now all we have to do is find b, and I'll change colors. So b is going to be our s squared term. So we have, let me do that on the top. I can do it in pink. So here we have a bs squared, and so we also have negative 2cs squared. So now we can write that, and here we have a negative 2. So we can say that negative 2, or we go ahead and write the other ones first. We can have b minus 2c is equal to negative 2. And so it must be, since c is equal to 1, we have b minus 2 is equal to negative 2, and we have b is equal to 0. Okay, so here we match the coefficients of s squared, and here we matched the coefficients of s cubed. Okay, so let's see what we have. So we have that f of s is equal to 7s cubed minus 2, s squared minus 3s plus 6, all divided by that denominator, s cubed multiplied by s minus 2, and we have a negative 3 over s cubed plus 1 divided by s plus 6 divided by s minus 2. Again, we had b equal to 0, so we have no denominator, no term with a denominator of s squared. And so now let's take a look at our table, the right side of our table. We can see here that the inverse transform of f and this will be of t, is equal to, we'll go ahead and deal with this term first. Of course, we are pretty comfortable with that right now. Negative 3/2 t squared plus, of course, we know that this is 1, plus 6e to the 2t. So let's write a few details here. We have here, we have that f of t equal to e to the at, has the transform, Laplace transform, of 1 divided by s minus a. So you can see here that we have a equal to 2. Okay, and then by linearity, we will have this 6 here. So this is e to the at, which is what we did here. Okay. Now, looking at the 1 over s, we're pretty familiar with that. when f of t is equal to 1, we have 1 divided by s is our Laplace transform. And our next one here, just move this over here. If we have f of t is equal to n factorial over s to the n plus 1, we know that our, n factorial over s to the n plus 1, which is what we have there. Of course, we have a coefficient of -3. We have t to the n power. So you can see here that n is equal to 2. So we would need a 2 factorial in the numerator. And so that's where we come up with the 2 in the denominator. And then our -3 is that coefficient. And that concludes this video.